Okay, let's compute a double integral. As we transition into double integrals, we actually get to use the technique we've been using before, and that's basically Fubini's theorem. As I've stated over here, by Fubini, the double integral is the iterated integral. And when we get to triple integrals, we will continue to do iterated integrals. So that's a really, really landmark theorem, which tells us that the process of integration by iteration is actually very good. It gives us double integrals, it gives us triple integrals, and so we weren't wasting our time when we were learning that process. So for instance, here's an actual double integral here. We have the integral I, we have the function y divided by x squared plus y squared, integrated over the region R. And then dA simply replaces the differential dx dy as an area element. So this is a very general expression of a double integral. Okay, so now we have to step back and look to see that R here, the region of integration, is designated here. That is, x runs between 1 and 2, and y runs between x and 2x. And so what we can do is use Fubini and write I with this representation of R. So the outer integral would run from 1 to 2. The inner integral would run from x to 2x. And so now what I've written here is actually good. We saw with the last problem that we needed to switch the order of integration. But notice here, this is very useful if we actually start with y, because we basically get a du over u, which is the natural log antiderivative. So this is a very useful order, and we will stick with that. But the only issue here is the chain rule. We've got the y squared here, so when we differentiate, we need a 2y here. So let's go ahead and fix that. We'll put in the 2 and pay for it. So now this is table ready relative to the y integration. So when we integrate, we just get the du over u, which is the natural log of the u. So we have natural log of x squared plus y squared. We don't need the absolute values here because clearly the x squared plus y squared is non-negative, so there's no reason to use absolute values. Now we can say, all right, well, fundamental theorem says we need to substitute with the upper limit 2x and the lower limit x for the y variable. So when we do that, we're going to get, in our first argument, x squared plus a 4x squared, and in the second argument, we get x squared plus x squared. But that's easy to simplify in the same process. So here the argument of the logarithm is 5x squared, and here it's 2x squared. But of course now we use our definition of an identity, an equation that's true for all values of the variables for which it is defined. So we want to use that identity for the logarithm function here to write this as a log of a quotient. So now we can see a really nice simplification. The x squares will absorb, and we're just left with natural log of 5/2, which again is a constant which we can factor. So all these nice properties that we enjoyed in Calculus 1 and Calculus 2 are enjoyed by the double integral and eventually the triple integral. So all these linearity properties that we've been using without thinking about it, we can now do with these. So rest assured that if you use any of them, they are valid. So now the last integral is just 1 relative to x from 2 to 1, and that just gives us this. And of course 2 minus 1 is 1. So when we actually write this in, we have 1/2 times the natural log of 5/2. And we are done.